Hello everyone. In this video, we're going to be solving an exponential trigonometric or maybe an exponentially trigonometric or trigonometrically exponential equation. We have tangent x to the power cosine squared of x, and that is equal to cotangent of x to the power sine of x. And we're going to be solving for x values. I'm also going to show you a graph and results from Wolfram Alpha, which I think is pretty interesting. So first of all, notice that in this expression, the bases are different. By the way, I just made a post about my new schedule for my two other channels, the Shorts channel and the aplusbi. Hopefully that'll work. I'll try to post 4 times a week, Monday, Wednesday, and what was the third one? Monday, Wednesday, Friday, and Sunday. Okay, I think that's what it is. Anyways, I'll let you know. So to be able to solve an equation like this, and by the way, what is a plus bi? It's a channel about complex numbers. Go ahead and check it out if you haven't done so. So to solve this problem, we first want the bases to be equal. So that's going to be the first thing, okay? Tangent x, cotangent x. The bases are different, but yet they're related. How? Well, if you know a little bit of trigonometry, hopefully, even with the basics, you should know that cotangent x is 1 over tangent x. In other words, cotangent is a cofunction, but at the same time, it is the reciprocal. It's not always the case. Cosine is not the reciprocal of sine. That would be nice if that were the case, but unfortunately that's not the case. But cotangent and tangent are reciprocals, and you probably also know that cotangent can be written as cosine x over sine x, and tangent x can be written as sine x over cosine x, which we could use here, but I have a better idea. Since cotangent can be written as 1 over tangent x, why don't we go ahead and make that replacement on the right-hand side? Okay, so we have tangent x to the power cosine squared, and that is equal to cotangent x to the power sine of x. Let's go ahead and replace this cotangent with 1 over tangent. And now that gives us tangent x to the power cosine squared of x equals 1 over tangent x to the power sine of x. Awesome. Now, they still don't have the same base, but one thing to keep in mind, rules of exponents or rules of exponentiation, whatever you call it, 1 over tangent x can be written as tangent x to the power -1. You probably know that, right? And then, of course, I want to raise it to the power sine of x. And the left-hand side will be unchanged. Now notice that these two are exponents and can be multiplied. So that gives us tangent x to the power cosine squared x. And now when you multiply these, you get tangent x to the power negative sine of x. Great. Now we got the same base, and then we can go ahead and do a couple different things. One is what happens when a to the b is equal to a to the c. We can safely say that b equals c is a solution. But that's not the only case, because if a is 1, think about it, if a is 1, then b and c don't matter, right? Because 1 to any power will be satisfied. Or if a is -1, then b and c have to be even, right? So in this case, we don't necessarily have to have b equals c. Does that make sense? So for example, -1 to the power 10 and -1 to the power 2 are the same, even though their exponents are different, okay? Because of the special base. So we kind of need to check all these 3 cases. Let's go ahead and start with case number 1. Let's call this number 1, let's call this number 2, and let's call this number 3. For the first case, we want b equals c. So in other words, cosine squared of x equals negative sine of x. Remember, we had the -1 from the reciprocal. Now, this equation can be solved by since sine and cosine are different kinds. Let's go ahead and use the Pythagorean identity and write the cosine squared as 1 minus sine squared. And where does this come from? This comes from the identity sine squared x plus cosine squared x equals 1, which is very important. Now, this gives us a quadratic equation. Let's put everything on the right-hand side. Sine squared x minus sine x minus 1 equals 0. And if you just call sine x s, usually that's pretty common, then you get s squared minus s minus 1 equals 0. And from here, we can find the solutions. What are they? From the quadratic formula, negative b plus minus the square root of b squared, 1 plus 4, which is 5. Does that remind you of the golden ratio? Yes, it should. Now, one thing to keep in mind, though, there are two s values. And since root 5 is greater than 1, this will be greater than 1. Makes sense? If you do 1 plus 1 divided by 2, that'll be 1. Anything greater than 1 will produce something. Why is this important? Because sine x, if x is real, cannot be greater than 1. So we can't accept that solution. What about this one? Could this be less than negative 1? Now, think about it this way. In order for this to be less than negative 1, 1 minus root 5 needed to be less than negative 2, and root 5 needed to be greater than 3. But that's not true. Therefore, all of these are false. Make sense? Because they're kind of like double-sided, sort of. Or we can go in either direction. So this solution, the second one, should be acceptable. Okay? But it is negative. 1 minus root 5 over. And if you also think about it, I think root 5 is about 2.3 roughly. So this is about, and I think this is also 1 minus the golden ratio, is it? I believe so. I think it should be like this, right? Yep. So it should be like 1 minus 1.6 something. And that just becomes what? Negative 0.4. So this is roughly negative 0.4, negative 2/5 if you want to write it that way too. So why am I looking for the value? Well, sine is negative. What about cosine? That's a good question. And you can actually find it from this equation. If sine x is equal to this, you should be able to find cosine from here. But guess what? There are two possible values. That's what's interesting about this equation. Now, here's what I'm going to do. If sine x is equal to 1 minus root 5 over 2, then from here I can basically find x by arc sining both sides, right? Arc sine 1 minus root 5 over 2. You got to be careful though. Arc sine has an image, or should I say not the domain, but the range. Yes, the range should be here for the arc sine. So whenever you have a negative value, your answer must be between negative pi over 2 and 0. Make sense? So in other words, x is between negative pi over 2 and 0. Under those conditions, I mean, whatever the values. Of course, you need a calculator to find this, but I'm going to show you a bunch of different values. Now let's go and look at the other cases. For example, can we have a 1 at the base? Is that possible? Let's take a look. If this is true, then we said that, okay, after that we went into this, right? I think we got negative sine x from here, right? So now we said that, okay, the exponents don't have to be equal to each other. We could also have that the bases are both 1. And it's quite possible if tangent x is equal to 1, then from here x can be pi over 4 or 5 pi over 4. Of course, I'm only considering the values that are between 0 and 2 pi. But if you wanted to write it as a general solution, you can add multiples of 2 pi to it, or to both, okay? But these should be fine for now. Now, this works, but what about negative 1? So the problem with negative 1, and let me tell you what it is. If tangent x is negative 1, then x must be 3 pi over 4 or 7 pi over 4, right? Wait a minute, did I write 3 pi over 7? Unbelievable. 3 pi over 4 and 7 pi over 4. And if you, let's say you use 3 pi over 4. If x is 3 pi over 4, cosine squared 3 pi over 4 is going to be 1/2, and that's going to be very problematic. You know what? You're going to be raising negative 1 to a fractional power, which is not real. But can we find complex solutions? That's a really good question. And you can kind of think about it and let me know what you think. And also, if x is equal to 3 pi over 4, on the right-hand side, we're going to have negative root 2 over 2. So negative 1 to the power 1/2 and negative 1 to the power root 2 over 2. And I think that's a negative. Is it a negative? Let's think about it. 3 pi over 4 will give you a negative tangent. And if you negate it, it'll be positive. So that's good. It's going to be a positive sign. But notice that these two are not equal because this one is not defined in the real world. And this one is not defined in the real world either. But in the complex world, they might have a meaning. Okay? So we're just going to stick with the real solutions for now. And that's what we get. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.